So hello students, in this video we are going to learn about a special case of Graham's law, a special case of effusion of gases. We know that several polyatomic gas molecules never remains in pure form. They always remains partially dissociated, and in some cases they remains partially associated also. In that cases, the rate of effusion changes according to their extent of dissociation and association. So let us take an example of gas where dissociation always takes place. The most common example is phosphorus pentachloride gas. If we take phosphorus pentachloride gas in a flask, it never remains in pure form. It remains partially dissociated, and the dissociation can be written like this: PCl5 gas giving PCl3 gas plus Cl2 gas. To account for this dissociation or association during effusion, the first step we need to do is to find out the average molar mass of mixture in terms of degree of dissociation. So if alpha is the degree of dissociation of PCl5, degree of dissociation, we know that moles of reactant decomposed out of its 1 mole. So if alpha is the degree of dissociation, then out of 1 mole, alpha mole will be dissociated. On the other side, alpha mole of PCl3 and Cl2 gas would be formed. So number of moles at equilibrium will be sum of all these, and that will be 1 plus alpha. So if we start with 1 mole, the equilibrium mixture will have 1 plus alpha mole. We'll have to take it practically that in a flask we started with 1 mole PCl5, and 1 mole PCl5 will have mass equal to molar mass of PCl5. Now no matter whether gas decomposes or associate, if it is sealed, the total mass is not going to change. So even at equilibrium, mass of the gas mixture will be equal to m naught. But now the mole has changed. Initially we started with 1 mole, now we have 1 plus alpha mole. And we know that molar mass is mass upon number of moles. So in this case we have mixture. We express the average molar mass of mixture by this m bar, which will be equal to mass of the mixture, which will be mass of pure PCl5, mass of 1 mole of pure PCl5, and it will be m naught divided by moles 1 plus alpha at equilibrium. That is how we determine average molar mass of mixture first. So in case of dissociation, we first write the dissociation, equilibrium, and we balance it for 1 mole of reactant. So that here we'll have 1 and we'll be subtracting alpha from 1. And then the moment we write here 1 indicates that we are starting with 1 mole of reactant. So numerator will always have mass equal to mass of 1 mole of reactant, and denominator total moles of gases at equilibrium starting with 1 mole of reactant. So obviously this average molar mass will be less than m naught because denominator is greater than 1, and we know that the rate of effusion is inversely related to square root of molar mass. So due to this dissociation, molar mass is decreasing, so rate of effusion will increase. Similarly, if we take a case of association, suppose we put some NO2 in a flask which dimerizes to say N2O4 gas. For balancing 1 by 2, be very careful, we are taking 1 mole on this side. This is a case of association. And now let alpha mole is associated, so alpha by 2 mole of this will be formed, and at equilibrium N total number of moles will be 1 minus alpha plus alpha by 2, so it is 1 minus alpha by 2. And in this case, average molar mass of the mixture will be mass of the mixture divided by moles of the mixture, and mass of the mixture will be mass of 1 mole of NO2, which is m naught divided by 1 minus alpha by 2. This quantity will be greater than m naught since denominator is less than 1, and therefore due to this association average molar mass will increase and rate of effusion is inversely related to square root of molar mass, therefore rate of effusion will decrease. So in case of association, rate of effusion decreases. In case of dissociation, rate of effusion increases. Now, how do we account all these things in carrying out calculation? So let us take a case of effusion through a numerical problem. We have been given a question that a partially dissociated equilibrium mixture of PCl5, PCl3 and chlorine gas effuses 2 times slower than pure oxygen gas at same temperature from the same pinhole at same pressure. Determine percentage dissociation. Determine percentage dissociation of PCl5 gas. Percentage dissociation of PCl5 gas. The condition given is that a rate of dissociation, rate of effusion of O2 upon a rate of effusion of mixture is 2. Mixture is 2 times slower, so oxygen is 2 times faster, and that will be equal to average molar mass of the mixture divided by molar mass of oxygen, which is 32. So average molar mass of the mixture will be 4 into 32, which is 128. Now the equilibrium mixture is PCl5 gas decomposed to PCl3 gas plus Cl2 gas. So 1 minus alpha, 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 and total at equilibrium 1 plus alpha. So average molar mass, which is 128, will be equal to m naught divided by 1 plus alpha. M naught is PCl for PCl5 molar mass is 208.5 upon 1 plus alpha. So alpha will be equal to 208.5 divided by 128 minus 1. So it will be 80.5 divided by 128. So if we solve it, it comes out to be approximately 0.63. 0.63. This implies in equilibrium mixture around 63% of PCl5 gas is decomposed. Let us take one more situation. The question is that oxygen is always partially ozonized. A sample of partially ozonized oxygen effuses 0.9 times slower than pure oxygen gas under identical condition. Determine mass percentage of ozone in ozonized oxygen. This is a case of association. Here oxygen is associated partially to ozone. If we balance it, 3O2 will give 2O3. But be very careful that we will be starting calculation for 1 mole of oxygen only. So if alpha mole is associated out of its 1 mole, 3 gives 2, so 1 will give 2 by 3, so alpha will give 2 by 3 alpha mole of ozone. So total, N total will be equal to sum of all this. So it will be 1 minus alpha plus 2 by 3 alpha. So 1 minus alpha by 3. That is the number of moles of equilibrium system starting with 1 mole of oxygen. Also given that rate of effusion of ozonized sample of oxygen is 0.9 times slower. So we can say that rate of effusion of ozonized mixture upon rate of effusion of pure oxygen is 0.9, and that will be equal to molar mass of pure oxygen, which is 32 upon average molar mass of the mixture. So average molar mass of the ozonized sample of oxygen will be equal to 32 divided by 0.81, and that will be equal to 32 divided by 1 minus alpha by 3. It is the total number of moles. So here average molar mass will be 32 divided by 1 minus alpha by 3. So 32 will cancel out, giving 1 minus alpha by 3 is equal to 0.81. So alpha will be equal to 0.19 into 3, that is 0.57. So 57% of oxygen is ozonized. So ozonized oxygen is 57%. Now if we start with 1 mole of oxygen, 1 mole of oxygen weigh 32 gram. Out of 32 gram, 0.57 into 32 gram has been converted into ozone. So mass of ozone will be 32 into 0.57 gram. But total mass of mixture will still be 32 gram due to conservation of mass. So mass percentage of ozone will be equal to mass of ozone 32 into 0.57 divided by total mass into 100, which is 57%. So this mixture contains 57% of ozone. So that is how we proceed for the case of dissociation and association accompanying the gaseous